When you go to the modules and you go to the tests, right now, practice problems for the final, that's posted. I'm going to go through them right now. I also decided this, I'm kind of redesigning how the tests work so that I can make unique versions of the tests for everyone. There is a final practice test that you can look at. And how this works is there's basically one of each one of the analyses that we've done in the class and the probability. I wanted to include that too. So there's one question pulled from the probability. There's one question from the conditional probability. There's one correlation, one simple regression, one multiple regression, one z-test, a one sample t-test, independent samples t-test, paired samples, one-way ANOVA, repeated measures ANOVA, and then the two-way ANOVA. At least for this semester, the two-way ANOVA is not on the final, but I just included it to just go through it anyways. Just you can see it if you wanted to. So on that practice final test, it will pull, randomly pull one from the ANOVA. I don't know how many I have in there now, and it's just going to randomly pick one. And you can take this practice test one time and you'll be able to see exactly, at least the format, the layout of the test, exactly how it'll be. And it's like, if you mess up the one-way ANOVA, it's like you should maybe go back and work on that a little bit, or whichever the test is. The probability, some people do have problems with the conditional probability, I noticed. So anyways, go through these practice problems like I'm about ready to do, and then you can also take a practice final test, and that should prepare you pretty well for the final. We'll go to the practice problems. Let's see, how did I set it up? I actually took these questions from some things we'd already done. I am trying to, and so one way by building this test bank is the data set will be included right there. And so you would just copy and paste this over into either SPSS or Excel, and then you won't even have to open up a file. You'll just copy and paste it over. Okay, so let's preview it. Is there a relationship between age and cognitive development? So let's put it into SPSS. So copy, Control C. One thing about it, so I'm going through this now, sometimes when you paste them over from SPSS, when you paste over numbers into SPSS, it doesn't see them as a number. And if you were trying to run an analysis and it's not working, what you need to do is go to the variable view and see what it says there. So if it says type string, that means it thinks it's letters, and we don't need that for a correlation. So we'll change that to numeric instead of string. When you do change that, make sure to go over to this measure, and if it says something like nominal, you want to change that to scale. Almost everything we've done in the class is scale. Okay, so we've got our two variables there. Analyze, correlate, bivariate. We'll move both those over. Like if I was taking the test, this is how I would do it. I would have that there. I'd put this, I have two different screens. Usually I'd separate them like that. But anyways, the R, the first one's the degrees of freedom. If it says 12, your n's 12, it's not 12. The degrees of freedom is 10, because for correlation, it's n minus 2. Our value for R, 0.62, and our p-value is 0.03, so it's less than 0.05. Okay, I just pasted it over into the Excel sheet. You used to have to drag these down, but now it updates automatically, and so if you put in a smaller data set, it'll take out these away. If you put in a bigger data set, it will create the calculations there. You don't technically need those calculations there, but I do think it's kind of fun to see how what's going on underneath the hood. If we come over here, we get in green are the numbers that you actually need, and if we see, same numbers. So it gives you the n. This one actually gives you the degrees of freedom, which SPSS does not. You don't need the t-value, but if you were going to go look it up, you could look up values for t, and you can see we got a 2.46, and you would look up that critical value, and you'd get your p-value from that. But yeah, all looks the same. All right, what's next? Okay, this is a z-test. We are taking a sample mean that we have, and we're going to compare it against what we consider to be a population mean. So it's like the mean cost for an upscale kitchen remodel is like $66,500. We're doing this in Chicago, and we got 68,900 with a standard deviation of 15,800. And this is from 16 homeowners. So you would take all those, and I'll show you how to do it. You can do this by hand. I can't remember if you can do it in Excel or SPSS or not. I think I tried to. It was too difficult. It's like it was just easier to do it by hand. But you could also do it in this Excel sheet as well. So our sample mean, our sample is 68,900. The population is 66,500. The standard deviation was 15,800, and our n was 16. Okay, great. So our z-test was a 0.60. If you remember from the z-test, we need to get at least a plus or minus 1.96. So this is not going to be significant. what was the result of the test. This is just what is the value for Z, and it is 0.61. Remember to have the leading zero if it can go above 1. I know some people are still not on board with that. Please do that because it will count it wrong if you put in 0.61. It's proper APA style. Okay, what do we have? Okay, these are the probability ones. So GRE scores for grad school applicants are shown below. Randomly select one applicant between 700 and 749. Okay, well, the first thing you have to do is find out what your total is. So we'd add up all of those numbers, 7 plus 4 plus 5 plus 4. Okay, so we got 55. We're just going to look between 700 and 749. That's just 4 divided by 55. 4 divided by 55. We'll get a 0.07. Probabilities, they cannot go above, even though the calculator is going to show you a 0. With these numbers, a proportion, a percentage cannot go above 1.00. So we don't have leading zeros. Between 450 and 499, that is 10 divided by 55, 18.18. Between 600 and 699, so this is the addition rule, 669, 699, so 5 plus 4 divided by 55.16. Randomly select one applicant. They scored 700 above or less than 400. We don't have less than 400, so it's kind of a tricky question, kind of. What was it above 700 and above? 750 and above, so 7 divided by 55, 0.13. What are the chances of picking 2 students in a row from 500 to 549, right? Yeah. This is the multiplication rule. So the first one is 10. So 10 divided by 55 gives you 0.18. So 0.18 times 0.18, 0.03. The chances of picking 2 students between that number, about 3%. Okay, conditional probability. Okay, so I created a little, you could do it by hand on a piece of paper. I like doing it in Excel. I just copied this. So quizzes, no quizzes, good or poor understanding. This is the conditional probability. So there's 2 different things going on. We know our total is going to be 100. It says that somewhere. Oh yeah, the very first statement, 100. Okay. 50 students completed the quizzes in preparation for the test. So quizzes, total, 50. 40 of those said they had a good understanding of the material. So 40 there. Let's see, of the remaining students. So how many are remaining? Well, there's 100 total, and we had 50 in the quiz. That means there's 50 in the no quiz. Some people got this wrong on the tests. They're putting in strange numbers. So how many are remaining? There's 50. 45 said they did not understand it well. So poor 45. And then you can fill out the other numbers. You're just adding them up. So if there's 50 at the bottom for the total and there's 45 there, it means there's 5 there. If there's 40 there, 50 there, it means that has to be a 10. And then you can double check it. It's like it should add up correctly going down. It should add up correctly going across as well. So if we put a 45 here, and then 10 plus 45 is 55. 45 plus 55, 100. Okay, so what's the probability of randomly selecting a student who understands the material well? Good understanding, we go to the total. 45 divided by 100.45. Probability of selecting a student who completed the quiz, we go to quizzes, total, 50.50. If your number was 100, you would have to divide whatever that number is by your total. But for this one, it's pretty easy since it's 100. Conditional probability, good understanding, given that they took the quizzes. Given that is going to be your denominator. So taking the quizzes, 50 is the denominator. Good understanding is 40. 40 divided by 50.90. Conditional probability, student poor understanding of the material given they did not the quizzes. Okay, so no quizzes is our denominator. Poor understanding, 45. So 45 divided by 50 gives you 0.90, which now I think about it, on the other one, the one right above that, 40 and 50, which means we need to go back up here because it cannot be the same. I messed up here. 40 divided by 50 is 0.80, not 90. That's how it happens, though. It's like you're taking the test and you're going to miss a couple just because you make a kind of a silly mistake. Okay, do absences predict grades? If you see the word predict, that means we're talking about a regression. And since it's one variable predicting one other variable, we are talking about a simple regression. So you can copy that over. So we have grades and absences. A simple regression. Analyze, regression, linear. And then we are going to move So we are saying that our grades are dependent upon how many absences you have. So grades go in the dependent, absences go in the independent. It's like absences is deciding what your grade is going to be essentially. Click OK, at least for this one. Okay, significant regression was found. Our degrees of freedom, which are 1 and 38. Our F statistic is 58.20. Our P is less than 0.001, and our R squared was 0.61. No leading zero on R squared, or P values. There we go. Okay, these are IQ scores for incoming freshmen. We have reason to believe this class will have an IQ higher than 110. We have our sample. We're comparing it against this hypothesized mean. We think it's going to be higher. Analyze, compare means, one sample t-test. And we are going to move over, this is variable 11. We're going to put in our test value, which I believe was 110. And because we said higher than, we're saying it's a one-tail. Click options and change 95 to 90. Click continue, click OK. We get, okay, our IQ was significantly higher than 110 was our test value. And then we list our mean, which is 124. Our standard deviation is 11.00. Confidence intervals, 90%, you see it there, but it is 95%. We're just tricking SPSS. Our lower is 7.63. Our upper is 20.37. Our T, the degrees of freedom, right there, is 9 for the degrees of freedom. Our actual T statistic is 4.03. And P is less than, we did a one tail. It's not actually less than 0.001. I'm going to put in 0.001, but I wouldn't be surprised if it's 0.01. If it is, I will change that to an equal sign instead of less than to make it 0.001. Okay, moving right along. I copied all this over for, if you're using SPSS, you don't need this group 1 and group 2 and the EPO and the control. It's for the Excel sheet for people that want to use that. And maybe I'll show you that one, this one in Excel as well. This is, we give one group EPO and test endurance scores against a control group. This is 2 independent groups, so we'll do an independent samples t-test. Analyze, compare means, independent samples. Group 1 and 2, that is our, that one there, that's our grouping variable. Click define groups, we've got 1 and 2, and then we'll move endurance over to our test value. Yeah, as mentioned in class, there's a significant amount of research that says that EPO increases endurance, and in that case, we would run a one tail. So options, again, changing it to 90. Click OK. There we go. So the mean difference of, we get that from, scroll over just a bit, right there, 5.5, 5.50. Confidence intervals are just a little bit to the right of that. So 1.94 and 9.06. Our degrees of freedom, right there, 10. Our value for T is 2.80. Our p-value for the one tail, it's 0.009. That means it's less than 0.01. And our Cohen's D comes from, Cohen's D, right there, the point estimate 1.62. For some reason, I'll never get some people on board. It's not the standardizer. That's what we're using for the equation. But this is the point estimate. It's the actual Cohen's D. Grades 1 and grades 2. It's just like as soon as I see that, it's like that's probably a pre-test, post-test, meaning it's paired samples. We discussed these in class. As a refresher, grades 1 is taking the final on the first day of class compared to taking the final on the last day of class. I will change the instructions on that. We discussed how it could be one tail or two tail. We discussed how it could be one tail or two tail. I do think I did it as a one tail, but in the instructions for the final, I will put in exactly, this is a one tail. I won't even be tricky where you have to think about the T-horn or any of that stuff. It's just like, this is a one tail. Analyze, compare means, paired samples t-test. And we'll move those two variables over, grades and grades 2. Click options, change that to 90, click continue, click OK. On average, they scored lower on the pretest. So there's our means right there. This one's 63 for the pretest, 0.58. And then 80, our standard deviation is 11.78. And then our mean in the second group is 88.92 and 10.29. the difference of 25.33. It's right there. Confidence intervals are right here. Most of the time we're going to report these as positive numbers. So if you see negative 29, negative 21, you got to flip that and have 21.03 first. And then 29.64. The smaller number goes first. So if it's negative 29, negative 21, then it is negative 29 first. But when we flip it, it's 21 and 29. It was significant. Same thing with the other ones. Our degrees of freedom, 11. Our t-statistic, 10.57. Our p-value, less than 0.001. And our point estimate, our Cohen's d, right there, 3.05. Okay, comparing regression scores for people deprived of sleep for 0, 24, and 48. Parent 3 group means, that means we're doing an ANOVA. I've noticed sometimes when I copy and paste these over, it's something to do with the table. It doesn't, SPSS doesn't like it, but if you just leave one letter off there, it does it just fine. So copy, and then I paste with variable names. And so yeah, it worked fine. You just don't have the first letter of it. But when you don't, I don't know, there's something about it doesn't like. In SPSS, you don't need these, but you would in the Excel sheet. For SPSS, how we would do that is analyze, compare means, one-way ANOVA. The group is our grouping variable, or group, as we have it now, or grouping variable or factor. And then grades, and then DV is our variable for regression. Post hoc, I believe it says to do two keys. So the first 2 keys, not the second one. Click continue, and then options, get your descriptives. I like a means plot, you don't have to do it. And then make sure that's checked, and then click OK. This one I'm going to do in the Excel sheet so you can see what it looks like. Now we go to the one-way ANOVA. This had 3 levels. We're going to paste, make sure to clear out the old data. So you can just go delete cells, shift up, and it'll get rid of all that old data. So first it asks for the means and the standard deviations for each group. They're right there, means, standard deviations. I put the ones in green that you're probably going to need. So 2.00, standard deviation 1.00. For 24, it is 4.67 and 1.53, and then 8.33 and 2.31. They do differ significantly. You get your degrees of freedom right here. So your degrees of freedom, your F statistic, the p-value, 2 and 6 and 10.50 and p less than 0.05. It's 0.01 something, so it's not less than 0.01, but it is less than 0.05. And then our eta squared is right underneath that, 0.78. According to Tukey's, okay, so our mean difference, this is the one we're looking at right there, 0 to 48, 6.33, and then it's asking for the Tukey's. So we need to make sure to get the confidence intervals for Tukey. It says lower Tukey, then upper Tukey, 2.08 and 10.59. In the future, I might just go all Bonferroni and just not even worry about doing Tukey's. The next one, we're doing a repeated measures, because now it's going to be the same people, but we're going to just test them at 3 different times. So 0, 24, and 48. It's 3 different levels. So if you go to the Excel sheet, it's repeated measures ANOVA, the 3. We'll post that up there. Okay, and so just like with the other one, we list the means and the standard deviations first. 3.00, 1.00, 4.67, 1.53, 8.00, and 2.00. This is where we get all our stuff for the ANOVA. Our degrees of freedom are first, which are 2 and 4. Our F statistic, 10.00. The p-value, less than 0.05. And the eta squared is 0.83. I know it lists a 0, but we don't. However, none of the comparisons are significant when using a Bonferroni correction. And all you have to do here is put in the sign the right way. So p is greater than 0.05. Okay, this one's not going to be on this, at least for this semester. This is not on the test, but I'm going to do it in case maybe I decide to include it in future tests. This is a 2A ANOVA, a 2x2, because we have two different crops and two different waters. We're looking at crop yield. Okay, if I was to look at this, what I'd look at first are, so we do have main effects. Main effect for fertilizer, main effect for water, we see that right there. The interaction, we see that fertilizer times water, it's significant as well, meaning that we can now go look at the pairwise comparisons. It's like, you know, maybe it depends on what your like research angle is, but it's like maybe you would report that water 1 had a difference with fertilizer 1 and fertilizer 2, or maybe you're looking at more from the fertilizer point of view and it's like there's a difference with fertilizer 1 with water 1 and 2. And all you have to do for this though is like look at the answer. So it says water 1 and fertilizer 1 had the worst yield, and when using a Bonferroni correction, water 1 and fertilizer 1 compared to water 2 and fertilizer 1. And so that's going to be, okay, let's see if I can fill these in right. So there's a main effect for fertilizer type. Again, all the main effects and interactions are right there. 1 and 36. F is 24.73. P 0.001. Eta squared is 0.41. For the water, it is 1 and 36 and 36.94. P less than 0.001, and the eta squared on that one is 0.36. And then for our interaction, it is 1 and 36 again. Our F is 36.94. P less than 0.001, and our eta squared is 0.51. Okay, and so yeah, using Bonferroni, water 1 and fertilizer 1. Water 1 and fertilizer 1. We can get that from up here. It was a 2 point right there at the top. 2.20, standard deviation 0.92. That's significantly worse than water 2. So 7.00 and 1.76. The mean difference, we get that from down here. Or you could just do it in your head, but 4.80, P less than 0.001. We should maybe have the confidence intervals there, but it's okay. All right, another one. So I think we're almost done. This is a multiple regression. So we're seeing if poverty and house value can predict crime. So copy. Go over here to SPSS. Click paste with variable names. So we're going to analyze regression, linear, and we are saying, can it predict crime? So crime is going to be our DV, and then poverty and house value is going to be our independent variable. Click OK. Significant regression equation was found. We're going to get all of that from this table right here. So it's 2 and 7. For the degrees of freedom, our F 8.63, P less than 0.05. R squared from the table right above that, 0.71. Crime increased. This is from the coefficients table. 0.46 for each increase in poverty. Our p-value for that is less than 0.05. So right there, 0.46, and then this is our, if it's significant or not. And it increased 0.46 for each increase in house value. And in this one, it says P equals, because it's not P less than 0.05. P actually equals on this one 0.07. Sometimes you can report 0.07 as marginally significant, but also there's a little bit more leniency on reporting coefficients that are not significant. Okay, let's see how we do. Okay, yeah, I made a couple mistakes. I mean, it just happens. On our correlation, 0.615 is 0.62. Okay, I got this from the Excel sheet. And it does round to 0.61. Sometimes SPSS does some weird things with the rounding, and so that's okay. I'll go in, and whenever it does the weird things to the rounding, don't worry about it. I'll make it where the key actually takes in both answers. On the next one, totally my fault. Again, you're just going to make mistakes like this. I did not put the negative sign. It doesn't say reported as a positive. And with the z-test, we put that our sample mean first. And so, yeah, should have put a negative number. I'll go in the instructions and say that explicitly to list it as a negative number. Okay, and yeah, this was the other one. I was wondering what that would say, if it would be 0.001 or 0.01. And so, yeah, technically it is less than 0.01. But what I'm going to do is change that less than sign to an equal sign. So it's like it equals, you can see that over there, 0.01. This is actually miskeyed. So that should be a 10.995 does round to 11.00. So I'll change that in the key. This one. It was just another one of those mistakes, just like everybody, we all make them. I did not have the following zeros. And so, yeah, I think that's it. So really, it's just a couple of mistakes between SPSS and the Excel sheet. And then a couple of, I just made mistakes. I should have had a negative sign there, and I should have had the following zeros there. I will go through each test. I've been doing that. I go through each test, and some of those things, it's like I check and make sure. It's like, did the Excel sheet round it slightly differently than SPSS? In those cases, I will fix those. I don't plan on fixing these though. If you don't put the following zeros, it's not right technically. So, okay, wow, that's a lot of stuff. I don't know. It took me, if I wasn't talking through it, this is maybe 30 minutes for me, but 30 minutes for me, for some people, it's going to be a really long time. What it should be is it should be about 2 hours long. That's how long a final is supposed to be. So like an in-class test is supposed to be 1 hour, but for the finals, they schedule it out for 2 hours. So it's supposed to be about 2 hours. I believe that most people will finish this in under 2 hours. I do think if I had the 2A ANOVA, that would push quite a few people over that 2 hour mark. And that's why I don't include it. I think this is enough to get us to 2 hours to keep everybody under 2 hours is my thought. Okay, I hope that helps. You can go through this and do the practice problems yourself. And then also there's a practice test. You can go through and take it. There may be some slight miskeys. And again, I'll go through and fix those. This is the first time we've used these finals with the fill in the blanks. And so we don't know what's wrong until we go through it the first time. Okay, I think that's it. Thank you for listening.